Okay, I don't think I've assigned much recently. So good. That's good because we need to get through some stuff so I can assign some new homework. Um, so we are working on displacements and statically indeterminate structures. And the way I'm going to do it, I'm going to start out by talking about um, elongation. Um, that has to do with axial loads and temperature changes. And then from that, we'll use the idea of elongation to talk about statically indeterminate structures. And then we'll talk about deflection. Um, and deflection is caused by bending moments. Um, you could also think of it as caused by shear forces. Those are related by their derivative relationship. And after we talk about deflection, we'll do statically indeterminate structures. And then we'll do angle of twist. That has to do with torques. And we could talk about statically indeterminate structures, but I don't think that's something that I don't think we do any problems like that. But you could keep, thinking about it in this way. So it's just all these ways that you can have the entire structure change its measurable shape, a displacement at the end of the beam or something. It can go, beam can stretch or contract, it can deflect up or down, it can twist, and you can use all those things to figure out at the current state of loading, what's the position of that thing, and you can use that for statically indeterminate structures. Yes, all of these use the internal loads to calculate these. What we talked about last time was so we're still talking about elongation. Due to axial loads. And we had this overall formula that said the change in length was equal to an integral over the whole length of the internal tension dx over EA. And then if you have a piecewise constant member, you can do this as the sum over all the individual pieces of TILI over EIAI. Just the number of pieces. So and there's another way that you can have elongation or contraction, and that is changes in temperature. So now length changes due to temperature changes. And this is a simple formula. The elongation due to thermal expansion or contraction, that's the T, is equal to a constant alpha times the length times the change in temperature, where this alpha is the coefficient of thermal expansion. That's just something you look up for a material. If you increase the temperature, that leads to an increase in the length. And if you decrease the temperature, that leads to a decrease in the length. And that works for any length measurement. We're talking about solids here, but there's a similar equation for thermal expansion of liquids. And the sort of related relationship between temperature and size for a gas is the ideal gas law. And so when I say it works for any length measurement, think about a material like this. So for example, let's say that you have like a torus-shaped material. What happens if you increase the temperature of that? What happens to this length? Well, if you increase the temperature, every length measurement gets bigger. Not that much bigger, but that's the idea. And that means that on the inside here, you might sort of convince yourself, if you think about it, like, oh, well, if it gets bigger, then that fills in the gap a little bit or whatever. But this length gets bigger just like any other length measurement. Okay. So you could, not the thickness, because you could, if you think of this as the thickness, after the deformation, that's a length measurement, so that's going to go up too. So proportional, that's right. Yep, exactly. Yep. And things get complicated if that's fixed to the ground or something, because then you have weird stresses and stuff. Okay, so let's do a calculation now where we'll combine the expansion or contraction that happens from axial loads with the expansion or contraction that happens with a change in temperature. So let's say we have steam thing. And let's say that we have a force of, I can't read what that says. Who wrote this? Okay. Let's say that this is fixed. And let's say that there is an 8,000 Newton force here. And let's say that the cross-sectional area of this, so we're talking about these cross-sectional areas. For the fatter piece, the cross-sectional area is 0.01 meters squared. And for the thinner piece, the cross-sectional area is 0.003 meters squared. And let's say that besides, oh, there's an 8,000 here, and I'm missing one. There's also a 5,000 Newton force acting here. And we'll think of that as a distributed load that's really happening around that whole sort of rim area. And then while these loads are applied, let's say that there is also a change in temperature. So this all happens while the temperature increases 100 degrees Celsius. We will say that this material is copper. And so the Young's modulus is 110 times 10 to the 9th pascals. And the coefficient of thermal expansion is 1.0 times 10 to the minus 5th. You can get the units from this equation. You know, meters is equal to all this stuff. Oh, I'm not doing that. You could, though. 1 over degrees Celsius. So what's the elongation of the beam compared to resting length? Okay, so does everyone have a picture of what's going on here? So applying these axial forces is going to, it's going to stretch this whole thing some amount. Increasing the temperature to 100 degrees Celsius is going to make the thing expand some amount, which is also going to make it stretch some amount. We're going to add up those two amounts, and that will give us a total amount of elongation. Yes? Oh, that's a really good question. Not that amount of temperature, but yes, there is a bit of an effect. But 100 degrees Celsius for like a metal is not very much.
Changing as well, right?
So, can you explain a little more, like what?
So Young's modulus would change.
Yeah.
Depending on the temperature.
Right.
Being hotter and hotter. Right?
Yeah. So I guess you'd want the Young's modulus at the final temperature, whatever that would be, and that's also something you could just look up in a table. Oh, you can't calculate it that way. Someone else has already calculated it by doing a tensile test of this material. So you wouldn't do it during this calculation. You would do it from a tensile test that you did previously before you needed to use the Young's modulus. You just heat the material up and do a tensile test. Okay. So first thing we have to do is figure out the internal loads. So the very first thing we have to do is figure out the external loads. And so free body diagram of this whole thing. The only loads we care about are axial. So I'm just not even going to put anything else in here. So there is a reaction force. There's a 5,000 Newton force here, 8,000 Newton force here. And those all add up to 0. So Newton's second law says, I'm just using the x component. It says positive R plus 5,000 plus 8,000 is equal to 0. So R is equal to negative 13,000 newtons. And so now rewrite this free body diagram. And we know we have a 13,000 Newton force this way, 5,000 Newton force this way, 8,000 here. So that's what we're starting with. And now we want to calculate the internal load. How many cuts do we need? 2, that's right. Yeah, sure. Are there? Okay, so cut 1. Oh, did I give lengths to these? We need lengths. I didn't. Stupid. Okay, so this is supposed to be 0.4 meters, and this is supposed to be 0.3 meters. And so cut 1 is for x values between 0 and 0.4. So we have the 13,000 Newton force on the left. And we haven't gotten to any of the other external loads, so now we just have a T this way. And so Newton's second law component says negative 13,000 plus T is equal to 0. So T is equal to 13,000. And so that's the internal tension for that whole first half, for that first part. Any questions about that? So I didn't put a shear force or a bending moment or a torque because this problem doesn't deal with any of that stuff. But if you did calculate those, they just all come out to be 0. And then cut 2 is for x values from 0.4 to 0.7. And this time we have 13,000 this way, 5,000 this way, and the internal tension. The thickness? No, that does not have any effect on the internal loads. It is going to have an effect on the elongation. But for the internal loads, we have never worried for that about the thickness of the beams. And so Newton's second law, x component says negative 13,000 plus 5,000 plus T is equal to 0. So T is equal to positive 8,000 newtons. And now the elongation that's due to those axial forces is the elongation for the first part, the first 0.4. So that's going to be positive 13,000 times the length of that first piece, 0.4, divided by the Young's modulus, 110 times 10 to the minus 9 times the cross-sectional area, 0.01, plus the elongation of the second part. And the second part is positive 8,000 times the length of that second part is 0.3 times the Young's modulus, 110 times 10 to the, oh, this should not be minus 9, this should be positive 9. That would be a very stretchy material. There, I minus 9 up here. No. And then the cross-sectional area of the second piece is 0.003. And if you calculate that, you get 1.2 times 10 to the minus 5. Without change in temperature, this is how much the beam would stretch. And now we have to deal with the elongation due to the temperature increase. The thermal expansion is equal to the coefficient of thermal expansion, 1 times 10 to the minus 5, times the length. Now this one we can do all at once. We don't have to break it up into pieces. This is just 0.7. Times the change in temperature. This increased 100 degrees Celsius, so this is a positive 100. If it decreased, that would be negative. And you get a value of 7.0 times 10 to the minus 4 meters. And so the total elongation is 1.2 times 10 to the minus 5 plus, I'll write this as 70 times 10 to the minus 5. And so you get 71.2 times 10 to the minus 5 meters. And it's positive, so that means it's, the length increased. Any questions about that? Okay. What? Just adding them together? Yeah, so you can just add those two together. So you could have problems where there are only loads causing the elongation or contraction, only thermal changes, or both of them. Just add them together. Yep. Yes, that's right. And no, okay. So no, so if those loads were trying to squish it, and you also increase the temperature, you'd get a squish this way and an elongation due to the temperature change, and those would offset each other. So in other words, if you if you wanted to keep the length the same while you applied a compression to something, you could raise the temperature. Or if you knew the temperature was going to say decrease and you wanted to keep it the same length, you could apply a you could apply an axial force to stretch it, and those will offset. Yeah. Yes. And when we talk about, so right now we're going to do statically indeterminate stuff, and yeah, there are definitely cases where um, you would use one of those two things to offset the other, so you don't get big forces applied by, like when it gets cold or whatever. So now we're going to use elongation and contraction for statically indeterminate structures. Um, and the steps that we're going to take, I guess this is just two steps, but first you're going to do the statics. All the equations that you can out of the statics. From Newton's laws. Then use the elongation contraction equations to create the necessary constraint equations. Okay, so when you use Newton's second law, or any Newton's laws talking about it generally, you're going to have more variables than equations. So really, you don't even have to recognize whether a system is statically indeterminate when you start it. If you go through the statics and you can solve it, it's statically determinate, and you're good. If you go through Newton's laws, go through the statics, and you can't solve it, you have too many variables, then you're going to look for a way to use those displacement equations to come up with constraints. Okay, so let me just do this as an example. Let's say we have a floor and a ceiling with a bar connected to both of them. And at the midpoint, we're applying a force of 20,000 newtons. And actually, let's move this away from the midpoint. It'll be more interesting. Let's move it down to a quarter of the way towards the floor. So 20,000 Newton force there. And this distance is 0.75 meters, and this one is 0.25 meters. And let's say for the whole thing, the cross-sectional area is 0.01 meters squared. And we want to know what are the reactions at the floor and the ceiling. Well, the first step is, this is a pretty simple one, and it's not too hard to see, at least when you get some practice with these, that this is statically indeterminate. But like I said, you don't have to see that right off the bat. Let's just start by doing the statics. So the statics says, I guess I'm going to lie it flat to do it, just because, no, I'm not. We'll do that later. Let's just imagine that this is a statics problem. Your idiot boss says, do the statics on this. Doesn't realize it's statically indeterminate. Stupid idiot. You know that guy. That guy, Dave. Always bragging about his Trans Am. Okay, so let's say there's a reaction force here, RA, 20,000 Newton force here, and then a reaction force here, RB. And you can tell I didn't make any effort to guess the directions of these reactions. I just put them in the positive Y direction. The signs will work out on their own. And really, like, this is just such a simple statics problem. Everything's happening axially. That's why, these are fixed joints. You would normally represent this as a full force vector and a couple and all that stuff. But that's all everything's going to come out to be zero except the axial components. So sort of a simplified approach to this. And now I'm going to use Newton's second law, the Y direction only. And so it says RA minus 20,000 plus RB is equal to 0. Rearrange it, and you get your one statics equation that says RA plus RB is equal to 20,000. So there's no more statics you can do. I mean, we could use the Y equation and the moment equation, but we just get 0 equals 0. So this is the only useful statics equation. And it gives one equation for two variables. And so now this is the point where you know it's statically indeterminate. That's the definition of statically indeterminate. Yeah. Okay, so if you wrote out Newton's second law, and you could use the x equation, the y equation, and then you did the moment equation, that gave you a third one. What you get is the y equation gives you this. The x equation gives you 0 equals 0. The moment equation gives you 0 equals 0. And so you end up with only one useful equation, and there's two unknowns in that equation. So when you're done with all the statics, you see you have a system that you can't solve. You have one equation for two variables, okay? And that's when you say that's the definition of statically indeterminate. You've gone through all the statics and you have more variables than unknowns. More variables than equations, sorry. Variables and unknowns are the same. Okay, so now we need more. And the extra information we're going to get, so we're going to get the constraint equations from the elongation or contraction. Okay, so now we need an expression for that delta. So we're going to find an expression for delta that uses these variables RA and RB. And now I'm going to lie it flat because we're used to doing internal loads with the thing flat. So this is the beam. We have the 20,000 Newton force this way. RA is this way. RB is this way. So I kept all the directions the same in term compared to the beam. I just laid it flat. And so how many cuts do we have to make? In order to calculate expressions for delta, we need to calculate the internal loads. Yep, so 2 cuts. So cut 1 is for x values between 0 and 0.25. So we have RA here. We haven't gotten to the 20,000 yet, so the only other thing we have is the internal tension. And Newton's second law in what I'm calling X now, it used to be Y, says RA plus T is equal to 0. So T is equal to negative RA. Now we'll go to cut 2. And this is for X values from 0.25 to 0.1. So this time we have RA here. We have RB here. This is not RB, this is the 20,000. We haven't gotten to RB, that's out on the right somewhere. And then we have the internal tension here. Yep. Right. Yep. So Newton's second law in the X direction says RA minus 20,000 plus T is equal to 0. And so the internal tension on that second cut is equal to 20,000 minus RA. Okay. Yes. This is only valid on that first cut. This is valid on the second cut. And so now we're going to calculate the total elongation by using that for the first 0.25 meters and that for the last 0.75 meters. Yeah. Okay, so now our total elongation is equal to, you can think of it as T1 times L1 over E1 A1 plus T2 L2 over E2 A2. And so that's equal to, on that first 2.5 meters, T is equal to negative RA. L is equal to 0.25. I didn't say anything about the material, so I'll just leave that as A. And leave that as E. And then the cross-sectional area is 0.01. And then the elongation for the second piece is the quantity 20,000 minus RA. The length of the second piece is 0.75. We don't know the Young's modulus, so that's just E. And the cross-sectional area is the same, 0.01. Okay, so we have this expression. Now the question is, how do we use this expression for the elongation to give us a constraint equation? So let's look back at the original thing. Assuming that the ceiling and the floor are not movable, okay, that those are fixed, what's the actual total elongation of this beam going to be? 0, yep. Inside, there can be, this point will move a little bit, every point in here will move a little bit, but the total length of this beam has to stay 0, okay? Anybody have any questions about that? There's always going to be some geometric requirement about the length or the deflection later on or the angle of twist that'll let us calculate that. So the floor and the ceiling don't move. So delta is equal to 0. And so our constraint equation, we're just going to set all this stuff equal to 0. We have negative RA times 0.25 divided by E times 0.01 plus the quantity 20,000 minus RA times 0.75 divided by E times 0.01 is equal to 0. And we can cancel a bunch of stuff. Divide both sides by 0.01 E. And we get an equation that says 20,000 oh no, not 0.5. So 20,000 times 0.75 is 15,000 minus 0.25 minus 0.75 RA. So that just comes out to be RA is equal to 0. Okay, so our statics equation up here, I'll call that equation star. Here's our constraint equation, the one we got from statics, the first step. And so now star and 2 star are 2 equations for 2 variables, and we can solve it. So equation 2 star says RA is equal to 15,000. Equation 1 star says the sum of these two is 20,000. So RB is 5,000. And so if I put it back into the original free body diagram, we figured out, so there's this 20,000 Newton force here. There's a force at the base of 15,000 up. there's a force at the ceiling of 5,000 up. And, you know, you can plan the fasteners accordingly. And notice that that didn't depend on the type of material. And even though I gave a cross-sectional area, it didn't depend on the cross-sectional area either. Sometimes it will. If you're combining loads, axial loads, and changes in temperature, that stuff will always come into it. If you're just doing things that involve loads like this, you might notice it's just related to proportionally how far that load is up or down on the member. But we can do the same thing with, you know, I could have done this with a beam that had different cross sections at different parts, and I could have added a change in temperature. Either way, you just come up with the whole equation for the elongation, fit it into whatever geometric requirement you have. In this case, that the total elongation is 0, and that gives you the other equation you need to solve. Yep.
So when we first started talking about this elongation formula, we talked about how we can use the summation as constant TPA.
Yeah.
But we don't have, at least in this one, we don't have constant T. Is that not really a problem?
It's piecewise constant. That's the thing.
Okay.
So it doesn't have to be constant over the whole thing. It just has to be piecewise constant. We just have to be able to break it up into finite pieces to use the sum formula, wherever that is. This one. Okay. But yeah, we could. It wasn't constant, but we could break it up into 0.25 meters where it was constant and another 0.75 meters where it's constant. You only can't use that if it's varying continuously. Any other questions? Okay, that's all. See you whatever day comes next. Sometime in March. Hi. Good, how are you? Whatever month it is.